morning, sir. Myself, Shafiul Alam. My ID is 23535433, and today I will present my OBE assignment for digital logic and circuits. The problem is to design an automated system that tracks ICU bed occupancy in a hospital ward. The ward can accommodate B plus A plus H patients using my student ID B equal to 3, F equal to 4, and H equal to 3. So the capacity is 10 beds. The maximum capacity is set via a keypad. When all beds are full, a 7-segment display must continuously show the word full. When beds are available, another display bus must flash the words beds available. Entry and exit sensor provide admission and discharge pass. My task is divided into 4 parts. Moving to the next slide. The new slide, and first of all I am really sorry, sir, because my video are not working somehow and my laptop is something is wrong. So if I say the part 1, which is system block diagram and flow diagram. So the system's high level architecture is as follows: two sensor produce pulses, and entry pulse increment the counter and exit pulse decrement it. The counter is a 4-bit synchronous up-down counter because we need to represent 0 to 10, which requires 4 bits. A comparator continuously compresses the current count with the fixed capacity of 10, which is set via a keypad. On the right side, it shows the flowchart diagram, and on the left side, it will show the block diagram. In the comparator output device, a display controller. When the count equal or exceeded 10, the controller enables the first 555 timer that drives the full display in a steady mode. Otherwise, it enables the second 555 timer that derives the best available display in a blinking mode. The flow diagram on the right show that exact sequence of operation, which is sensor pooling, counter update, decision, and display update. This completes the first part of my assignment. Moving to the next slide. So the another part is internal design of the up or down counter with JK flip-flops. So now let me explain the internal design of the counter. I have used 4 JK flip-flops, which is Q3, Q2, Q1, and Q0 because 2 to the power 4 is 16. My state is 10 state. The counter is synchronous. All flip-flops share the same clock, so they change state simultaneously. The general rule for a synchronous binary up counter is J0, J0, K0 equal to 1 up, and J1, K1 equal to Q0, and J2, K2 equal to Q0, Q1, and J3, K3 equal to Q0, Q1, Q2. So in this left side, I will show the full diagram of JK flip-flop, and there will show the up and down counter equation. In the right side, I'll show the admission sensor is when up equal to 1 and discharge sensor is down when is 0. So I show the state chart diagram, which is the 4-bit state chart diagram, and showing the JK flip-flop table, which is 00 is 0 for J and K equal to don't care, 01 is J equal to 1 and K equal to don't care, and 10 don't care 1 and 11 equal to don't care 0. Moving to the next slide. So this is the second part of my OBE assignment, which is 555 timer for beds available blinking. So for second part, we must design two 555 timer circuit, one for steady full display and one for blinking beds available display. The problem kit formula for the blinking timer's duty, cycle, and frequency, which depend on my student ID. First, I compute P equal to A plus B plus D plus E plus G multiplied by 2, which, and substituting my value A equal to 2, B equal to 3, D equal to 3, E equal to 5, J equal to 3. So P equal to 16 into 2, which is 32 bit. Since P is less than 50, the duty cycle is 100 minus P equal to 68%. Next, the frequency. For frequency, A plus C plus 5, A plus C plus B, which is 12 Hertz, therefore the time period equal to 1 by F, which is 83.33 millisecond or 0.0833 second. And the load time is TL equal to T minus TH equal to 26.66 millisecond. And I select the capacitor, which is 50 microfarad from the allowed values, obviously, and using the 555 stable formulas, we know TL equal to 0.693 R2 into C. Here R2 value is come 26.66 millisecond and TH value comes, we know the TH formula is 0.693 into R1 plus R2 multiplied by C, which is R1 value is 870. Thus, for the blinking display, we use R1 870 ohm and R2 770 ohm and C equal to 50 microfarad. And we also verification with the duty cycle, and this produced 12 Hz square wave with 68% duty cycle, making the message bits available flash clearly. Moving to the next slide. In this slide, there is the extended part of part 2, which is 555 timer for display. So here the first timer is configured in stable mode with a diode modification to achieve near 100% duty cycle, which makes the full 7 segment display appear continuously lit. The second timer is also in a stable mode but designed with a 68% duty cycle and a frequency of 12 Hz calculated directly from my student ID. This causes the best available display to blink at a visible rate. All resistor and capacitors are clearly labeled and the two display are marked accordingly here. Moving to the next slide. Here is the last third part of our OBE assignment, which is FSM design for output A and B. So in part 3, we are asked to design an FSM that produce output A TH milliseconds and output B TL milliseconds with a clock period of 1 millisecond. Our calculated TH and TL from part 2 were 56.67 millisecond and 26.66 millisecond, but the problem instructs us to set any value greater than 4 to exactly 4. Therefore, both TH and TL become 4 millisecond with a 1 millisecond clock cycle. We need 4 clock cycles for A and 4 for B, repeating forever. Hence, the FSM has 8 states. So S not through S3 produce A equal to 1 and B equal to 0, which is shown in the right side state table. Also, we draw the state diagram for where is A is 1 and where is B is 1. So as I say, S not through S3 produce A equal to 1 and B equal to 0. So S4 through S7 produce A equal to 0 and B equal to 1. The state diagram shows a simple ring which is S0 to S1 to S3 to S4, S5, S6, S7, then is come to S0. I use binary state encoding with 3 flip-flops P2, P1 and P0. The next state logic is straightforward, but the question explicitly asks for only the output logic. Observing that the MSB is 0 for state S0 to S3 and 1 state for S4 to S7, we can write A equal to P2 bar and B equal to P2. That is the complete output code. A reset input is included to FSM initialize the FSM to S0, ensuring predictability, behavior and power up. So this is the part 3 which I demonstrate you. So moving to the next slide. Here is the part 4, which is limitation and modification for larger hospitals. The system has several drawbacks, like the discrete counter suffers from glitches and propagation delays also. Sensor may cause false counts due to mechanical bouncing without debouncing circuits. The 555 timers have plus minus 2% tolerance, and capacity leakage affects timing accuracy. The full display never achieves perfect 100% duty cycle. The system cannot recover from invalid state automatically. So this is here, and scaling to more than 10 bits requires additional flip-flops, increasing cost and complexity significantly. A microcontroller based design would be a more reliable alternative. Moving to the next slide. So this is the conclusion slide. So to conclude, I have presented a complete digital system for ICU bed occupancy monitoring. It includes a synchronous up or down counter with JK flip-flops, two 555 timer circuit, one for steady full and one for blinking beds available, and a simple Muri FSM for the output timing. I have also discussed the practical limitation and how the system could be upgraded for larger hospitals. So thank you for your attention. I'm really thank you, and I'm very much sorry because my video are not working, but completely I have discussed the whole OBE assignment according to the questions. Thank you so much, sir. Assalamu alaikum.